This is my first video in my module on small module on probabilities using the counting rules that we've covered, which would be the fundamental counting rule or multiplication rule, permutations and combination type situations, and how we could use those to help us calculate probabilities of situations that have an immense number of outcomes, okay, possible, so larger sample spaces. So the counting rules, which were are the multiplication, permutation, combination rules, they can be combined with probability rules to solve probability problems. Okay, so we say using the fundamental counting rule, permutation rules, and counting rule, we could compute the probability of a lot of different experiments. So as an example, I listed here a couple. We say such as getting a full house when 5 cards are dealt. You know, how many different ways that happen, or what's the likelihood of that happening, or say selecting a committee of say 3 women and 2 men to form a club consisting of 10 women and 10 men. Okay, so we can actually figure this out using our counting rules. So we're going to extend it into example number 1 here. So it says calculate the probability of getting 4 aces when 5 cards are drawn from an ordinary deck of cards. So the advice I have for us in this video at least is I'll write it up here, but number 1 is this, is draw out the sample space. So we say draw out the sample space. And remember, the sample space for an experiment is the set of all possible outcomes. So in terms of draw the sample space, here's what I mean by this. Let's draw at least some sort of like Venn diagram image. We say a number of possible ways to do this. Okay, so we say calculate the probability of getting 4 aces when 5 cards are drawn from an ordinary deck. Let's take a look at this. First of all, we say aces seems to be something we're concerned with. So we say ace. How many aces are in the deck? We'll put this in. We say 4. Okay, so we got 4 of those. And we say, well, an entire deck, we know that's sort of 52 total cards. So if ace is all I care about, we'll just call everything else other. And other, we say, well, then there must be 48 of these because there are 48 cards that are not aces for a grand total of 52. Well, it says when 5 cards are drawn from an ordinary deck, we say, well, you know, is this an instance where order matters or order doesn't matter, first of all? So when we calculate the total number of ways to do this, should I use a combination or a permutation? And, you know, when you consider a deck of cards, when you hold your cards in your hand, it doesn't really matter how many ways you do it. So now that we've got the sample space drawn, let's do this. We say calculate the size of the sample space. So we say sample space size. This is what we want to do. In other words, the total possible number of ways to get 5 cards from a deck of cards. So we say, all right, well, first of all, in this instance, that would say, oh, you know, combination, order doesn't matter. I have 52 cards, and I want to choose 5 of them. Okay, and this would, you know, represent the total number of ways there are to get 5 cards from a deck of 52 cards. And so I don't, on the calculator I don't have a combination thing, but you can see how this would be rather big. We could do it by hand, but I did open up a calculation permutation calculator down here. So we say 52 choose 5. We say, okay, well, I've got 52 things. I'm going to choose 5. We've got to set on combinations here. Calculate. So we've got 259, 89, 60. 259, 259. Come on now. Oops. 259, 89, 60. This is how many different 5-card hands we could get out of a deck of cards. When you calculate a probability, see, we say, you know, maybe it's like 4 aces when we draw 5 cards here. The first thing we do is calculate the sample space size. So we say out of 2,598,960 total ways. In other words, we got this here, 52 choose 5. And we actually would start with this. I just put up the answer in the basement right here, sorry, first. But we'd say, well, out of this many total ways to do it, now what we want to consider is this. What's the event that I get 4 aces when I draw, you know, like 5 cards, okay? So we say, well, I don't know, you know, let's look at it this way. We say I'm getting 5 total cards. Let's start with the aces. Now, if you go through a category of your sample space at a time, I promise you won't miss this. So we're going to start with the aces. We say, all right, I've got 4 aces now. How many of these aces do I want to get? Okay, and I want all 4 of them in this instance. So we say of the 4 aces, I want to choose all 4. Now we want a 5-card hand, so the important thing is this. We say, well, and then, so we're multiplying here. Of the 48 other cards, How many do we want? Well, I need one more card. This gives me 5 total cards. So one thing I want to mention about this before we calculate it is this. You'll see in the first instance here we say, all right, let me go a different color here. We say this 4 and this 48 that we drew from, so the 4 aces and the 48 other cards, they make up the total deck of cards, and they'll sum to this. And what if I switch over to a different color here? Let's go to like a green. Here we go, chartreuse. We say, all right, and I chose 4 aces and 1 other card, so how many total cards did I choose? Well, I chose 5 total. So this is always kind of a way this thing happens here, but we say we need 4, choose 4. So I'll get my calculator back out here. We say, all right, 4, choose 4. Think about it as 1, okay? You know, and I wasn't shocked to get this. We say this 4, choose 4 here. There's one possible way to do it. And the reason why is because if there's 4 cards, how many ways exist to choose all 4? Well, there's one way to do it, and that's to get all 4 of them. We say of the 48 other cards, how many ways exist to choose 1? I'll use my calculator to show you. Say 48, choosing 1, but basically you get 48, and the reason why, see 48, is because we say of the 48 other cards, how many ways exist to pull out 1 at a time? And so, well, there's 48 ways to do it, is to pull out each individual card on its own. So we get 48 out of this. Well, now I will pull out this calculator here. We say, well, how likely is that I get 4 aces when I draw 5 cards out of a deck of cards? Well, it's not very good. We say 48 divided by 2598960. You can see we get like 4 zeros and then 1846. So we get 0.00001846. This is very, very, very small chance. And think about it. You know, it's not going to be a very good chance you get 4 aces on your first 5-card hand. Okay. But yeah, this is how we carry this out. So you see this scheme a lot. You know, we say calculate the sample space. We did that on step 3. Step 2. Say step 3. Let me see if I can separate this here. Step 3 should have been calculate event space. We'll write this over this. We say size. And then step 4 was just like divide out. And as far as like calculate the event space size, we say 1 category at a time. What I mean by that is we went through each box up here in the Venn diagram. We said, okay, of the 4 aces, how many do I want? Of the 48 other ones, how many do I want? So we'll put this again to use in this example down here, and then we'll just start going a little bit quicker. We say a box contains 24 transistors, 4 of which are defective. So we say like N, you know, it's like N is 24 here. 4 are defective. Okay, it must mean the other 20 work or something, you know, right? We say if 4 are sold at random, so we're selling 4 at a time. We say find the following probabilities. So like total is R, you know, we're selling 4 at a time. We say exactly 2 are defective. So let's start with this. This is really important. You always start by writing down what you want to find. So for example, the probability, we say 2 are defective. You know, probability 2 are defective. Let's start with this. First things first, we say the first step up here was draw out the sample space. So of course this is what we want to be doing. We say here's my sample space. This is the set of 20. Always put the total down here. 24 total defectors. Transistors. We say 4 are defective. So we say here are my 4 defective ones, and we say the ones that work, it'd be the other 20. Okay. So now that we've got this, we say, well, how many possible ways exist in the first place to get 4 transistors from 24 transistors? So we're going to write this down here. We say 24, choosing 4. And we're using combinations because order doesn't matter. So now here's the deal. We say, well, what's the event then that I get exactly 2 defective? So here's the part where we're going to go through again. You know, after we calculated the sample space size, we're going to do step 3 up here. It says calculate the event space size 1 event at a time, 1 category at a time. So we're going to start with the defective ones here. We say, all right, well, of the 4 defective, how many do we think we want to get here? We say 2. So we say, all right, well, I've got 4, and I'm choosing 2 of those. And then, you know, we say, of the 20 that work, you know, how many of these do I want? Well, since we're getting 4 total, and I've already chosen 2 of them here, we say, of the other 20, I'm going to choose 2 of those. And so we just have to calculate these. As a matter of fact, that's the easy part. We've got calculators to do this for us. Of course, 4 choose 2. We'll go ahead and rip these out. We say, all right, 4 choose 2. Of course, we could still just use the formula for this. So we get 6 for this first slot. We say 20 choosing 2 at a time. How many ways it just exists to do this? We say 20 choosing 2. 190 ways to do this. You know, 190. So in this instance, we say 190 times 6 is 1140. So we say 1140. Now, we need to calculate the sample space size, which of course is going to be bigger. We say 24 choosing 4. We got 24 and then an N field here, and then 4 in the R field. 10, 6, 26. So we say, all right, so 10, 6, 26, okay, which is rather big. 10, 6, 26. We could figure this out, and I do want to figure this out. You should always put it in a calculator. We say 11,1140 divided by 10. Try it again. 1140 divided by, we have 10, 626. So we get this about a 10.73% chance. We say a 10.73% chance that we'll get 2 defective if this is the setup over here on the left. Okay, well, you know, that's kind of nice. It is not a bad thing to figure out. We say, again, you know, we figured out the sample space size. The nice thing is for the rest of these, the sample space size is going to stay the same. We're doing the same thing. We're taking, you know, 4 from the 24. So that'll stay the same on the bottom. We'll always get this 10, 6, 26 for the rest of these experiments. The top's going to change, but again, the top, we say, step 3 up here, calculate the event space size, one category at a time. Look, we just went through each little box over here, and we said of each one, how many do I want? So we're just going to piece this together for the rest of them. We say, okay, so no defective, no D. So we say no defective. That would mean that 1 could be defective, or, you know, or like actually no defective, none defective, all working. So let's try this again. We say, all right, out of our 10, 626, if we're savvy here, we say, let's look at the top. We say, of the 4 defective, how many do I want? Well, in this case, I say 4. Yes, but I want to choose none of them. And we say of the other 20 transistors, let's say 20 here, I want to choose all 4 of them from that batch. So we say, well, I need 4 choose 0, 4 choosing nothing. Now I'm going to come back over here and I'm going to ask my calculator, but for the sake of just think about this, how many ways exist to choose nothing? You know, to do nothing. And there's one way to do it. So 4 choose nothing, you know, if you were to write it out in the formula, you get 1. So in this instance, I get 1 on top, times now 20 choose 4. So we say 20. In this field, we say 4 in the R field. Calculate this, we say 48, 45. So 48, 45 on top, 48, 45, divided by our 10, 6, 26. And that's what we'll do here on our calculator. We say, so 4, 8, 4, 5, divided by 1, 0, 6, 2, 6. About 45.59, 45.60. So about a 45.60% chance. So it's pretty good that you're not going to get any defective, you know, and that makes sense looking at our setup over here on the left. Okay, so now in this instance, we say all defective. So we say, all right, probability all defective. We say 4 defective, you know, we say 4 defective. They mean the same thing. So we say, all right, well, out of this many ways to do it, to choose 4 from 24, we say, all right, let's go through a category at a time. So we say of the defective, of the 4 defective, we want how many this time? Well, of the 4 defective, I want all 4 defective. And then we say of the other 20 ones, I want to choose none of them. So again, you know, we say, okay, well, 4 choose 4. Well, think about this. How many ways exist to choose 4 things from 4 things? It should be 1. Throw it in the calculator just to prove it to you here. We get 1. Whoops. I want that button. We say 1. And then the same thing over here. We say, okay, well, 20 choose nothing. Well, there's one way to choose nothing. So it's really just 1 out of this many ways. And that's the reason why is because you say, well, how many ways exist to get all 4? There's only one way to get all 4 of them. So we say, all right, well, 1 out of 10, 6, 26 here. We'll get our calculator back out over here. 1 divided by 1, 0, 6, 2, 6. So we say a point 0.0000941. 0.0000941. Now the interesting thing is our probability here. So this is about, if you move this twice to the right, this is a 0.00941%. Okay. Probability. This last one down here says at least 1 is defective. Now this one's different. Now if I were to write this, I would say, well, probability greater than or equal to 1. Because think about this. At least 1 defective really means this. We say probability of 1 or 2 or 3 or 4. And, you know, being aware of our rules, addition rules from before, you know, we've used these. We say really it's the sum of these. Probability of 1 is defective, or probability 2 is defective, or probability 3 is defective, or probability 4 is defective. And really, instead of calculating all of these, here's what we could do. We could say, well, you know, I'm choosing 4 total, and this would be like 1, 2, 3, and 4. Why don't we just do this? If, you know, if this were to represent all the possible ways we could do this over here on the left, we'd say if I want the probability that 1 or 2 or 3 or 4 defective, we say number defective. You know, maybe what this represents, number of defective. We say, you notice I have 4 categories here, 0, 1, 2, 3, or 4. What we could do is, instead of finding out the probabilities of all of these, you know, say get this one, this one, this one, this one, add them up, we could say, why don't we just find this one and like cut it out of the total sample space, because we know the probability of the entire sample space is always 100%. So we can say probability of sample space minus the, you know, the probability of 0. That would leave behind all the green stuff, which is what we want. So in this case, we say, well, I don't know. What is the probability that I get no defective? The nice thing is we already found it, you guys. So we can say the probability of at least 1 defective. Really, we're going to use the idea of a complement of an event. So we say it's 1.00 minus 0.0000941. And we get approximately, we say, if I were to say minus 1, and then just make it positive again here. We say 0.9999905, so 0.999905, or a 99.9905% chance of occurring. And, if you think about this, it's probably a pretty good chance you're going to get at least one defective, given that there are some in the pool, So not very encouraging, but this is how you would use probabilities accounting rules. Cheers.